3.3, I'm going to talk you through iodometric titrations. So the titrations require thiosulfate, and they're called back reactions or back titrations, and we'll see why when I go through it. Okay, so you should now be seeing the screen. Okay, can I remind you that we now have a schedule, which is in our Google Schedule spreadsheet. It's a separate tab, okay, and it shows you when you need to be doing past papers. I'll bring that up in a second so you can see that. Okay, so here is the schedule coming up now. Okay, so here is the schedule. Okay, and then we've got our revision schedule here, and in the list here it says which papers you should be doing on which date. Okay, and obviously we're working up towards the exams. Okay, so there is this work on Starter for 10 and page 9 of this is actually now a red booklet. So let me just very quickly change that because you have got a red booklet this year. So let's go bang, 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 and RD. Okay, so it's a red booklet, which you should have collected from Reprographics Now. Okay, and obviously recap that if you get stuck on anything, come to the workshops on a Monday or a Tuesday. So we've already started to talk about oxidizing agents, and we need to think about what they could be. So what you should do is to stop the video now, okay, and you can list as many oxidizing agents as you can, okay. Right, so let's have a look at some of those oxidizing agents. So what have we got? We have got all of these things. What do you notice about them? Well, they are either things that are highly charged or have high oxidation numbers. So copper can be copper 2+, but it can be reduced to copper 1+ or +1. And when in doing so, it will then oxidize something else. But a lot of these oxidizing agents have got oxygen in or nitrogen. So nitrogen is quite a key one. All the halides can have like multiple oxidation states. They can be oxidizing agents, and of course we've got our good friends the manganate 7 ion and the dichromate 6 ion, where the chromium is 6+, and here in the manganese is +7. So all of those are good things that can do oxidizing. So you should have some. Here are some notes. Okay, oxidation. Obviously. Loss of electrons. The one way of thinking about it is the oxidation number increases if something is oxidized, if a species is oxidized, and the reduction if something has been reduced. So if we look at the iron here, it's +3 here. Here it's gone down to 0, so its number has reduced from +3 to 0. Just think of a number line. And here the carbon is +2. It's been oxidized to +4 here. Okay, and obviously this is summarizing what happens there. Okay, and obviously we've got our rules for balancing oxidizing agents, so redox reactions. So if you want to, you can just have a quick check of that. So you could stop the video and carry on when ready. Okay, so let's crack on. So we've got how do you recognize them? They can all be reduced. Okay, so if you think of something like the iodine here, the iodine is going to be +5. Because oxygen is always -2 in its compounds apart from peroxides. Okay, so it's -2, 3 of them, so that makes -6. Overall, the iodate ion is -1 here, so this iodine must be +5 to make the overall thing -1. So this is iodate 5, okay, but this one is iodate 7 because 4 lots of 2- is -8. It's -1 overall, so the iodine must be +7, its oxidation number is. So you can see how that works, and obviously we've got that written down here as well. Okay, we can see if things are, well, we're going to look at that's going to be really important when we come on to the electrode potentials in 23.4. Okay, so we're going through here. We're going to look at how we can do calculations with iodine and thiosulfate. And these are really crucial experiments. And so you may be given a structured calculation, so that's where the exam paper breaks it down into parts and you work through, or you can be given an unstructured one, so that's a longer answer question based on something like an experiment and you have to work it out. Okay, right, so let's have a look at direct titration. So what you've done so far have been direct. Okay, an analyte, okay, so that's what goes in your flask. Okay, you might have an aliquot of an analyte. So you might have a 25 centimeter cubed aliquot. That's, you know, an amount. Aliquot just basically means amount. Analyte is what you put in the flask. Titrant is what goes in the burette. Okay, so you wrap them together, you get products. And you might not know the concentration of the analyte, but you know the concentration of the titrant. You know how much volume you added, so you can work it out. So, for example, you could add sodium hydroxide to ethanoic acid. You get sodium ethanoate, okay, and you know how much sodium hydroxide you add. You know its concentration, its volume. Therefore, you can see this reacts 1 to 1, so you can work out the moles of ethanoic acid, and you know how volume is, so you'll be able to work it out its concentration. And this is all about because of stoichiometry. Fantastic word, stoichiometry. So that's a direct titration. Yeah, we know we add a certain amount of sodium hydroxide, we can calculate the ethanoic acid. Okay, so now we're going to go on to these titrations with iodine and thiosulfate. These are called back titrations. The reason being is that we react the species being analysed, the analyte, with a reagent, and this product, okay, reacts with a titrant of unknown concentration. So the reagent that we react our analyte with is not the titrant that is in the burette. Okay, so it's a back titration. So we have two steps, two equations going on. And iodometry is when we use titration of iodine. So we can react an oxidizing agent to iodide, and that will turn that into iodine. So we're going from -1 to 0. The iodide is being oxidized, okay? And so hopefully our analyte is going to be an oxidizing agent which can oxidize our iodide. And then our iodine is then can be titrated with thiosulfate. Okay, so it's not a direct titration. There are two reactions. We take our unknown, we react it with iodide, and we produce iodine. Okay, and then the iodine is reacted with thiosulfate, which we know its concentration. So we can, therefore, we can work out how much iodine we have got, and the iodine comes from reacting our analyte with our iodide. Okay, so it's a back titration. We can work out this, we work out that, and once we know this, we can work out this. Okay, that's why it's called a back titration, because we're going backwards to work out the analyte. So before we carry on, okay, what you need to do is read the textbook, okay, make notes on all this stuff here, okay, and then carry on. Okay, there's a little extension question there. So I'm going to stop. I'm going to ask you to stop the video. So stop the video and carry on when ready. Okay, so you should have made lots of notes about this. Okay, and we're going to go on and see how we could work out a equation of how this works. So, for instance, 30 centimeters cubed of bleach was added to excess iodide, okay, in dilute sulfuric acid. Bleach contains the chlorate ion. So this going to be an oxidizing agent? Well, yes, it is, because the chlorine, okay, is, well, the oxygen is -2. The whole thing is -1, so the chlorine is +1, hence chlorate 1. So the chlorate is a +1 oxidation state. It's going to be changed to Cl-, okay, in the presence of this. It's going to oxidize iodide to I2, and we're also going to make chloride ions. But the key thing is that the bleach, which is ClO-, okay, will oxidize iodide to iodine, and then we can work out how much iodine we get by reacting that with thiosulfate. So here is our first reaction. Chlorate plus iodide, okay, in the presence of acid, makes chloride plus iodine and water. Okay, so the iodine that's formed is then titrated against, and it works out that 29.45 centimeters cubed of 0.2 moles of sulfuric acid will react enough to remove all the iodide. Okay, so here we go. So we've got thiosulfate plus iodine makes 2 iodide plus the sulfate ion here. So calculate the moles of thiosulfate. So first off, what we're going to work out is we're going to work out the moles of thiosulfate, okay, from this data here. Okay, so the moles of thiosulfate is concentration times volume over 1,000. 1,000 because we've got it in centimeters cubed. Concentration times volume. Volume should be in decimeters cubed. Hence, we divide by 1,000 to get from centimeters cubed to decimeters cubed. And here we go. We get 5.89 times 10 to the minus 3 moles. Some of you should probably be able to work out that this is just 0.02945 dm cubed and won't need to divide by 1,000. Okay, so you can do it either way. Okay, so we've got the moles of thiosulfate. Now, calculate the moles of iodine used. Okay, so this is the thiosulfate moles. Well, this number of moles of thiosulfate reacts with this number of, well, the iodine, but the ratio is 2 to 1. Okay, so 2 moles of thiosulfate react with 1 mole of iodine. So therefore, the thiosulfate is this, the iodine must be half of this because it's 2 to 1. So there's the 2.945 times 10 to the minus 3 moles. Okay, so that's the moles of iodine that this has reacted with. But this iodine has come from this. Okay, so the iodine has been made by reacting with this. So the moles of iodide, yeah, well, let's have a look at this equation. Iodide is here, chlorate is here, so it's 1 to 1. So for every mole of iodine, we've got 1 mole of chlorate. So therefore, the moles of chlorate that we had originally is 2.945 times 10 to the minus 3 as well. Okay, so now we work out the concentration. Well, we need to go back and think, whoa, okay, we know the moles, but we need to know the volume. Aha, it's up here. Okay, so concentration is number of moles times volume over 1,000, or concentration is number of moles times volume if the volume is in decimeters cubed. Okay, so it is this here. Okay, I put those numbers all around. I think I put those numbers all around. Let's just move those over. So we'll just very quickly grab this one here. Gone. It's gone. And we need to copy that one across. This is slick, isn't it? Right, so let's pop that all back up. There we go. Okay, so that's now corrected. So we've got number of moles equals this, which is our number of moles, times our volume, which is 30 centimeters cubed, divided by 1,000. Okay, and that gives us that many moles per decimeter cubed. And that comes to 3SF. Okay. Right, so let's move on. So that's a structured question. The question has broken it down for you. So it's telling you to calculate the moles of thiosulfate, calculate moles of iodine, and then calculate the moles of chlorate, and then from that get the concentration of the chlorate. Okay, so yeah, those are the key bits of data, the volumes there. Okay, so now this is a practical. This is actually going to be practical 31, the last practical you do. It gives you a chance to do some research into copper and brass. So if you didn't really get a decent bit of research done when you do aspirin practical, this will help you to do that. So quantification of copper. So copper, as we saw, copper 2+ is an oxidizing agent. It's got 2+ here, it's a +2 ion. +2 oxidation number. It can react with iodide to make 2 CuI. The copper here is now +1 because iodide is -1, so there, so it's +1, -1, that's our copper iodide. Okay, so we've got that reaction there. Now, the iodine can then be reacted with thiosulfate, like we said before, and we can then get iodide, another sulfate ion, but the key thing is that this, we will know the amount of this that we use. Okay, so copper is the oxidizing agent. Now, what's quite nice about this is we've got a white precipitate. Okay, this is pale brown. Okay, so when you start to make this, you end up making what looks a bit like a cup of tea. Okay, so it looks a bit like a cup of tea, sort of a tea colour. Okay, and then the iodine then will react. It's in the conical flask. It's going to be pale brown. Okay, cup of tea coloured. It's going to go yellow. Okay, as it is made, and then it will go white. Once we have used all of the iodine up, we're just left with this white stuff. Yeah, so this is going to be pale brown. It looks like a cup of tea before the thiosulfate reacts with it. As the thiosulfate reacts with it, we're going to remove the iodine, which is pale brown, and leave the white precipitate. So it's going to be looking white, or pale yellow to white at the end. Okay. However, this can be a little bit tricky to see. So as you get close to it going white, what we can do is add a little bit of starch. Okay, and then the starch will make it go black, and then as soon as you've used up, got rid of the iodine, it will not be black anymore. Okay, so the thiosulfate is in the burette. It's a standard solution, we know its concentration. Okay, and we will then measure its volume because we got it in a burette. Okay, and the ion that we make is a tetrathionate ion. Okay, practice that. Okay, so what's the ratio of copper to thiosulfate? Okay, 2 moles of thiosulfate react with 1 mole of iodine, so 2 to 1. But 1 mole of this reacts with 2 moles of copper. So it's 2 to 1 to 2. So in effect, it's 2 to 2 or 1 to 1. So whatever the number of moles of thiosulfate you've got, it's going to be the same as the moles of copper 2 plus. Okay, so that's makes it a little bit easier. Okay, so we can prove that copper is an oxidizing agent. How many electrons are transferred? So we're going from +2 to +1. So the copper is gaining an electron, but it's gaining 2 electrons because there's 2 copper ions changing. Okay, so +2, that's -1. There the copper is +1. The iodide is -1 here, and it's 0 there. Now, can you see how that balances? That's why we need 4 iodide. So 2 of the iodides are staying as iodide here, and 2 of them are becoming iodine, and therefore they are being oxidized because they're going from -1 to 0. Okay, so copper is reduced, +2 to +1 reduced. Okay, iodine, or the iodine species is reduced, oxidized from -1 to 0. Okay, and that, well, there's 2 of them. Yeah, 2 of them are becoming I2, so they need to lose 2 electrons. Okay, and the copper needs to gain 2 electrons because 2 of them are going from +2 to +1. They need to add an electron to do that, 2 of them, hence this bit here, and it balances. Right, so when we're titrating this, okay, okay, so for instance, what you're going to do in your practicals, you're going to be given a brass rivet. Now, brass is made of copper and zinc, or the 2 main metals in it, copper being the main one. There are some other things, and that part of your research is to find out about brass. But that's a solid. It's not an ion, okay? So what we need to do is we need to react it with an acid. So we're going to react the copper with nitric acid. And the acid we're using is nitric acid. Let's see how we can make this a redox reaction. Well, okay, the nitrogen here, copper is S0. Copper here, it's joining to 2 nitrates, so this must be copper 2 plus. So the copper has gone from 0 to +2. It has been oxidized, okay? Now, there are 4 nitrates here. Only 2 of them are here. So 2 of the nitrates don't change. So those ones aren't changing. But 2 of them are changing because we're making nitrogen dioxide. So the nitrogen here, so this is NO3, it's -1. 3 lots of -2 is -6. The nitrogen here must be +5. And the nitrogen here must be +4. Okay, so this oxidation number for copper has gone up from 0 to +2. And 2 of the nitrogens that are in this here have gone from +5 down to +4, so they have been reduced. Okay, so +5 to +4, that one obviously doesn't change, it's still +5, the nitrogen is still +5, 0 to +2. Okay, copper oxidized from 0 to +2, 2 electrons are lost. Yeah, so there it is up there. So we've got a nice poisonous brown gas when this happens. And copper nitrate is a nice green solution. So what's going to happen when you do your practical is Gail will put, the technician will put the brass rivets into a flask in the fume cupboard with concentrated nitric acid. We'll get nice brown gas. We'll demonstrate doing one of them. And then the next lesson, once this has been done, you'll have a nice green solution, except that what we're going to do is we're going to add water to it. Okay, so we're going to dilute water, and this will form what's called a complex ion. And we'll do that in chapter 24, we'll talk about these. Here, this copper is actually making a dative bond. So dative, do you remember that? That's where one covalent atom shares two electrons with another atom. So this is actually a covalent bond, and 6 water molecules are surrounding the copper. Remember, oxygen has got lone pairs. Those lone pairs can be used to donate to the copper, so we form a dative bond here. This is an octahedral shape, so we'll come on to that when we do 24. So anyway, we've got this. This is what actually makes copper sulfate, or many copper compounds when dissolved in water, makes them look blue. Okay, and that's why copper sulfate is blue, because it's got lots of water in it. There is a video clip you can watch on that, and we will put links to those. Okay, so here is an example of an unstructured question to work out copper. So bronze is also an alloy of copper. It's different to brass. It's copper and tin. So it has different properties. But here's the bronze. Okay, we're going to analyze it to find how much of it is copper. So there is a bronze, a piece of bronze. Okay, it's 0.5 grams, so it's half a gram of bronze. React with nitric acid, and we get a solution which has got copper 2+ in it. And all that copper 2+ has come from however much copper is in the alloy. It's neutralized and reacted with iodine to produce iodine. The iodine was titrated with 0.2 mole of thiosulfate, 22.4 centimeters cubed of which were required. Calculate the percentage copper in bronze. So this is quite a multi-step thing that we have to work through. So first off, the first numbers we've got to look at are the thiosulfate and its volume, because that will tell us the number of moles of thiosulfate and therefore the number of moles of iodine. Remember that the moles of thiosulfate is also equivalent to the amount of copper moles. So we can write this down here. So we've got our equation. Here is the equation, the copper 2+ plus 2 electrons. And there's the equation to show it reacting with iodine to make iodine. And here is the thiosulfate reaction. It's well worth learning the thiosulfate iodine reaction, so you know what it is. Okay, so 2 of those react to make 1 of those, and 1 of those reacts with 2 of those. So the ratio is 2 to 2 or 1 to 1. Calculate the moles of thiosulfate. That's the first step. So we work out the moles of thiosulfate. So 0.2 times 22.4 over 1,000, or if you want to do it in your head, it's 0.0224, and you don't need to bother with the 1,000. Okay, there's our moles. That is also the reacting amount. So the reacting amount is 2 moles of copper makes 1 mole of iodine, which reacts to make 2 moles of thiosulfate. So it's 1 to 1 copper to thiosulfate, which we've got there. Okay, so therefore we can work out the moles of copper. Moles of copper is going to be the same as the moles of thiosulfate. So what is the mass of that many moles? Well, we need to do the number of moles times the AR, or the relative atomic mass of copper. Copper is 63.5, so multiply the moles by 63.5. That tells us that 0.28448 grams of our bronze was copper before it was reacted. So now we can do that divided by 0.5, which was our initial mass of bronze, times 100 to give us a percent. So it tells us that it's 56.9% to 3 significant figures. Why do we need to use 3 significant figures? I hear you cry. Well, I actually can't hear you because I'm probably nowhere near you. I'm in my house recording this. So why is it three significant figures, given that this value is got 5 decimal places to it? Well, we've got this to 3SF. So the 0.500 is 3SF, 0.200 is 3SF, this is 3SF. So all the values up in the question are 3SF. And that is basically it. So that's sort of explaining why it's 3SF, when even that is, that's to 4SF, isn't it? Okay, but obviously we need to go with the smallest. So that is it, okay? And obviously you should go through the textbook, answer the questions, do the examination questions in your booklet, okay? Or examination question on page 77 in the textbook. That's a structured example, okay? So lots of stuff for you to do. And this is what we covered in this session. Okay, so I'm going to stop the video and hopefully we will get a recording of it.